the percentage change in whatever it is that you measure is simply proportional to the percentage change in the size. So to be slightly more specific, roughly speaking, if you doubled the size of an organism from, say, 2 grams to 4 grams, or 2 kilograms to 4 kilograms, or whatever, doesn't matter where you begin, instead of doubling the amount of energy that is needed, even though you have twice as many cells to support, you actually only need 75% more, about 3/4 more. So there's a 25% savings, roughly, with each doubling of size. And that kind of systematic behavior is kind of amazing. And it was true across all taxonomic groups of organisms, whether you looked at mammals, birds, fish, crustacea, insects, and so forth. So that was surprising to me. But then I learned that it wasn't just true of metabolic rate. It was true of everything, essentially. I mean, almost anything that could be measured about an organism, anything that's kind of physiological. So something mundane like, the length of the aorta, the first tube that comes out of your heart, or something sophisticated like lifespan, or growth rate, time to maturity, or, diffusion rates of oxygen across membranes, whatever, it doesn't matter. But when these quantities are plotted in this way, they all have this similar power law behavior, and whatever this savings is always some simple multiple of 25% of a quarter. The number 1/4 dominated biology, and that is called quarter power scaling, in fact. So I became very intrigued about that, and I realized that to understand aging, which was the thing, and death, the thing I was interested in, I have to understand where the hell these laws come from, and then we can apply it to mortality.